Good morning. Let us quickly revise the electrochemistry part 2 in 10 minutes or 15 minutes. We have earlier studied there are two types of cells, electrolytic cells and galvanic cells. It deals with the electrochemistry 2 deals with the electrochemical cells, voltaic, or it also called voltaic cell, or it also called galvanic cell. For example, Daniel cell. The cell representation, you have studied earlier, the cell representation, the cell is represented, zinc electrode is immersed in zinc sulfate, and copper electrode is immersed in copper sulfate, and the double slash indicates the salt bridge. What is the role of salt bridge? Salt bridge is very important. Salt bridge is, we can easily make salt bridge by using a strip of filter paper and dip in saturated solution of KCl and ammonium nitrate. Okay, what is the importance of salt bridge? It is often asked in all the competitive examination, KCl, ammonium nitrate especially, because the ions of cations and anions should have equal mobility. Similarly, the transfer number is directly proportional to U plus, we have already studied, so it should be equal. Okay, why do we use salt bridge? Otherwise it prevents mechanical mixing of two solutions. Otherwise we have to mix, it will collapse. It will complete the electrical circuit. Otherwise you won't get, if you don't have salt bridge, you won't get voltage. Okay, it is a galvanic cell. It converts chemical energy into electrical energy. Electrical energy is produced, electric power is produced. Okay, it maintains electrical neutrality and it eliminates liquid junction potential. At the liquid, when you have two liquids at the liquid junction, there will be a potential developed. It eliminates liquid junction potential. Okay, in electrochemistry, this is the cell representation, and this is half cell, and this is another half cell. This is anode because zinc is oxidized to zinc ion, and copper gets reduced to, so this is anode, where oxidation takes place. This is cathode, the reduction takes place. The cell reactions are, the half cell reactions are, the cell reaction is this. Okay, so we have two electrons, it will get cancelled. In electrochemistry, the E cell, the standard EMF of the cell, is nothing but the EMF of the cell measured under standard condition, that is unit concentration and temperature 298 Kelvin and 1 atmospheric pressure. Okay, the standard reduction potential in electrochemistry, it will be confusing if you use oxidation potential, reduction potential. You always use standard reduction potential. That is advised by the scientist. You always use, otherwise you will confuse. Standard reduction potential. Although it is oxidized, you should use standard reduction potential. Therefore, E0 cell equal to E right minus E left, E cathode or E cathode minus E anode. Okay. Now we will calculate. See, before we calculate the EMF of the cell, we will go to an important topic: electrochemical series. What is electrochemical series? The values of standard redox potential are arranged in decreasing order, as you see, plus 2.87, and it is arranged in decreasing order. This is called electrochemical series. There are several questions asked based on this. It is also an important concept. For example, see, fluorine is at the top. It is an oxidizing agent. Therefore, if you go up, oxidizing power increases. Okay, oxidizing power increases. As you go down, the reducing power increases. Oxidizing power increases, and here reducing power increases as you go bottom, because sodium ion gives electron, so it will reduce. Reducing agent. For example, organic chemistry you are studying. And see, the platinum hydrogen H plus, this is electrode, and this is electrode reaction, and this is 0.0, it is assumed to be 0. See, above hydrogen, they are all oxidizing. Below hydrogen, they are reducing agent, reducing power. Okay, so this is the With respect to hydrogen, everything is compared. For example, the density of water is equal to density of, we compare the density with the water. Okay, now let us calculate. For example, here I have given the standard reduction potential of copper and the E right. Okay, copper E right. Therefore, this is equal to 0.34 minus, that is a left anode, standard reduction potential of minus, therefore plus minus of minus, therefore 7, therefore plus 1.1 volt. In actually, Daniel cell generates power of voltage 1.1 volt. Okay, if next, okay, let us now see the few other formulae used for solving problems to understand the basics. For example, the change in free energy is related to concentration. The change in free energy is related to concentration. It is obtained from thermodynamics. It is derived from thermodynamics. Delta G, change in free energy, standard change in free energy, or molar gas constant, temperature, reaction quotient. Q is quotient. Q is nothing but product by reactant. Product, the ratio of product divided by ratio of product to reactant. Okay. So what is the relation between change in free energy, EMF? Okay, the electrode potential, or we call EMF or electromotive force. Okay. So what is the relation between change in free energy and electrode potential? This is a standard condition, minus N of P, where N is the number of electrons involved in the cell reaction, and F is the Faraday 96,500 coulomb, E is the electrode potential in volt. Okay, next, Nernst equation. This is very important. There are several problems asked in IIT JAM, NEET, as well as in UG and PG, GATE, CSIR. Here, if you substitute, for example, you substitute this N of E in this equation. Okay, you substitute in this equation, and then you will get this equation. Okay, on simple mathematic manipulation, on substituting this, you will get E cell equal to E naught cell minus 0.059 N log 10 log to the base 10 product divided by reactant concentration. This is Q. Okay, now let us consider an example where we can demonstrate how Nernst equation is used to calculate the various parameters. For example, copper is oxidized, so copper will be this side and the silver will be silver with respect to redox potential. So it will be oxidizing. Here it will be different. Zinc, compared to zinc is oxidizing, zinc is oxidized. Here copper is oxidized and silver is reduced. So copper is oxidized 2 electron, therefore we will have to, silver gets reduced to silver, 2 electron is there, therefore multiplied by 2. So you will get the cell reaction 2. The number of electrons involved is 2 here because 2 electrons are involved. Let us substitute here E cell, E0 cell we can calculate from the electrochemical series. It is given in the Clark's table. Minus 0.059 divided by 2, 2 electrons are involved after the base 10. The product in this reaction, the concentration of product divided by the concentration of the reactant. The activity or the concentration of the solid substance is always equal to unity. Therefore, this will become 1, this will become 1. Therefore, it will be the ratio of copper 2 plus and silver concentration, square of the silver concentration. Okay, so it gives the relationship between the electron potential and the concentrations of the reactants and the products. Okay, next, maximum work done. What is the work done? For example, it produces energy. The cell produces energy. How much energy, how much work it produces? Therefore, minus delta G. It is given by again thermodynamics. Okay, we can calculate. For example, we can calculate for the Daniel cell Wmax equal to N of E, delta G equal to N minus N of E. Therefore, it will be plus. And for Daniel cell, how much maximum work done by the Daniel cell can be calculated 2 into 96,000 Faraday and coulomb. You always write unit along with the value in physical chemistry or in physics into 1.1 volt. Therefore, 1 joule equal to 1 volt into 1 coulomb. Therefore, joule. Therefore, this is the value and 212.3 kilojoule per coulomb. Okay. Now we are seeing up to this. Let us now discuss about equilibrium constant. Equilibrium constant is very important in chemical equilibrium. It gives the extent of the reaction, whether it how much extent it goes in the forward direction. For example, K value is large. K value is large. That means K value is large. The product concentration is large. Therefore, the extent of reaction is in the forward direction. So, how equilibrium constant can be calculated from the EMF of the cell, electrode potential. At equilibrium, the cell is dead. That is, the EMF of the cell equal to 0. Therefore, you substitute in the Nernst equation, you substitute 0. If you put 0, then E cell equal to 0.059 n log K. Okay, this is reaction coefficient. In this case, K equal to Q, because this is equilibrium condition. Under equilibrium condition, it will become equilibrium constant. The equilibrium constant can be calculated from the electrochemical series. Okay, theoretically we can calculate. Now, equilibrium, similarly, solubility product. Solubility product is again equilibrium constant of sparingly soluble salt. Dissociation constant of weak acid, that is also equilibrium constant. We can determine several applications. There are several applications of EMF by measuring the EMF of the cell, and we know from thermodynamics, second law of thermodynamics, delta G equal to delta H minus T delta S, where delta G is the change in free energy, change in enthalpy, change in heat content. We can calculate the thermodynamic parameters for this for various electrochemical reactions using the electrode potential. For example, delta G equal to, and delta S, you see delta S, this delta S according to thermodynamics equal to minus d delta G by dt. Here delta G equal to minus NFE. We know that if you put minus NFE dE by dt, because delta is the dE by dt, and we will get N of dE by dt. What is delta S? The change in entropy can be calculated if we know number of electrons involved. For example, in this 2 and Faraday constant, we know 96,000. We need to know dE by dt, temperature coefficient of the cell. What is temperature coefficient of the cell? dE by dt. Let us measure. You have a cell. Okay, you have a cell. You dip it in thermostat. You immerse in thermostat. You determine at 25 degree Kelvin, and you determine at 30 degree Kelvin. For example, you have T2 25 degree Kelvin, that is 298, and you increase by 10 degree, therefore 308. You determine the EMF of the potential. EMF of this is the voltmeter. We can measure the voltage produced. So you know E2 and E1 at two different temperatures. Then we can calculate the dE by dt. So we can easily calculate the delta S. Okay, delta S. Now, what is delta G? Delta G is nothing but NFE. You substitute NFE here. Okay, so delta S we know in this expression. Temperature is known. This is carried out at constant pressure, because at 1 atmospheric pressure at root normal pressure. Therefore, delta G equal to NFE. On rearranging the equation, you will get the delta H. Delta G also minus NFE we can calculate. So we can calculate the various thermodynamic parameters. So we have revised in a short time the electrochemistry part 2 based on electrochemical cells, voltaic cell, galvanic cells. Thank you for watching.